Chapter 5, Discrete Probability Distributions.
In this video, we'll learn about the Poisson distribution and how to apply it to decision-making situations.
So the Poisson distribution is where we want to figure out the probability of something occurring over space, time, or a well-defined segment or interval or unit of inspection. So the example I like to use to remember how to use Poisson is potholes. So if you've ever driven on a city street, you've noticed that there are potholes on the ground. And so Poisson, potholes, they both start with the letter P, so that makes it easier for me to remember. But if we think about a city street, that's a space or an area, and we can now use the Poisson distribution to determine the probability of hitting how many potholes. So here we see the symbol lambda, and this is the average number of successes or outcomes of interest in one segment. So using my pothole example, perhaps the average number of potholes is 3 in a city street. Now, with Poisson, the outcomes of interest are random because we're working with discrete random variables, and they're countable because you can count how many potholes are on a city street. Now, the probability that an outcome of interest occurs in a particular segment is the same for all segments. That's the assumption that we make. And when we're talking about how many segments we're studying, we'll denote it by the letter T. So it's really important that you remember that the two symbols that we'll be using with Poisson distribution is this lambda and the T. So let's look at what some examples would be if you were presented with a problem at work or on the homework or on an exam, and that you would know, oh, this is where we would use Poisson. So for instance, we wanted to know the number of patients who arrive at a hospital emergency room per hour. We can use Poisson to determine the probability of a certain number of patients that will arrive. This is important so that we know how many doctors and nurses or staff members we need to support our patients. Or for instance, we can apply Poisson to the number of calls a Dell tech support group receives in a 30-minute period. In this example, my segment is 30 minutes, whereas in my hospital example earlier, my segment was per hour. So the story that you're presented will tell you what your segment is. And again, in this example, it's important to know the probability of calls received in a particular 30-minute period so that we can staff accordingly. Another example would be the number of cars served at a gas station in a 24-hour period. In this example, now our segment is 24 hours. So you can see the segment is whatever we define it to be. And this might be useful so that we know how many pumps we need available at the gas station, staffing, how much gas to have on hand. And another instance is where we can use Poisson is the number of defects per square meter of leather. So if we think about raw material like leather, we can now estimate the probability of defects that you're going to see on the raw material. So here are the related formulas that you'll need when working with the Poisson distribution. So hopefully by now you'll notice a pattern is that with every kind of distribution that we're learning about, you'll always need to know how to calculate the mean or expected value, the standard deviation, as well as the probability distribution itself. So let's break down all the variables in our different formulas here. Again, we've got our lambda, which is our expected number or the average number of successes in one segment. And T is the number of segments we're interested in studying. So if we use my pothole example again, and our expected number of potholes on one street is 3, and say we want to study 5 city blocks, we would just take 3 times 5 for 15. Meaning when I study or I walk up and down my 5 city blocks, I should expect to see approximately 15 total potholes, or an average of 3 potholes per street. With the standard deviation, we simply take the square root of our lambda times t. And then for our probability distribution here, we have our lambda times t raised to the x power. So the x is the number of successes in t segments. So however many segments you're studying, and the X is the number of successes you're interested in finding. So remember, anytime you've got P with parentheses, that's the probability of some event. So whatever our event of interest is in our parentheses. So that's our X. The E here that you see in the formula is the base of a natural logarithm system. It's valued at 2.71828, but if you use your calculator, you'll just look for the button that says E and it will generate that number for you. Now, if for whatever reason your calculator does not have the E button, then you can manually enter 2.71828 to use the formula. Now, our natural log that we're using with E also has an exponent. In this case, you'll notice it's negative lambda t. So you still take the lambda t value from your expected value up here. You're just going to make it negative and use that as the exponent. When we multiply this across, and then we'll divide all of it by x factorial. Recall, factorial is where you take your number and you multiply it with everything after it. So again, factorial 4 is 4 times 3 times 2 times 1. But again, if you have a calculator with the factorial button, it will do this for you, so you don't have to do it manually. So when we look at the Poisson distribution, as you can see here, this is the distribution for the number of arrivals to a checkout section of your favorite store per hour. So here our segment is 1 hour. We are only looking at one segment, so our T is 1, and we're given our average number of arrivals to be 16 per hour. So as you can see, based on our distribution here, 16, which is my average in an hour, will be in towards the middle. When we look at the other possible number of customers on our distribution, the probability is illustrated by how high our bar goes. So for instance, if we wanted to know the probability of 26 customers arriving in an hour, we can see that it's a very low probability compared to, let's say, 16, because 16 is our average. Here, where we're using the actual formula for Poisson, if we wanted to know the likelihood of 12 people coming to the checkout stand in 1 hour, we would plug in our numbers into the formula where x equals 12. And so you can see here in our distribution, the probability of 12 customers is 0.0661 when graphed. But also when you plug it in the formula, that's what you get. Note that the shape of the Poisson distribution depends on your lambda and t combined. So here you can see when we multiply lambda and t together and the product is 0.5, our distribution looks different than, let's say, when our lambda t is 3.
Let's look at the steps to find our Poisson distribution. We first define the segment units. So we want to make sure we understand in our story what are we working with. Is it time, space, or volume? In step 2, we'll find our lambda, which is the mean of the random variable. In step 3, we need to determine our t, which is how many segments that we've identified in step 1. And then we will calculate by taking lambda multiplied by t. In step 4, we want to make sure we understand the problem and define the event of interest that we're going to solve for, and then we can use the Poisson formula or Excel to find the probability. So to use Excel for the Poisson distribution, you can use a formula, as stated here, where we have equals Poisson.dist, and in our parentheses we will have our x value, our mean, and our cumulative. Or you can use the formula builder in Excel. Recall that the formula builder defines each piece in case you don't remember. So this is good as a refresher if you would like to use the builder instead. Now, our x is the number of events that we're interested in knowing. Our mean that we use in Excel is the expected numeric value. So this is our lambda multiplied by t. So you have to do a little bit of math before you can use Excel. And then the cumulative determines the form of the function. So this is similar to what we've seen before in other distributions, where if it's true, that means our distribution is cumulative. That means it reads the area from left to right in our curve. If we type in false, that means we're looking for the probability of exactly a particular number of events. So let's look at problem 51 in the textbook. Arrivals to a bank ATM follow a Poisson distribution with a mean equal to 3 customers per 15 minutes. What is the probability that in a given 15-minute segment, one customer will arrive at the ATM? So first we need to dissect our problem. What is the segment unit defined in our story? In this case, it's every 15 minutes. The mean, or the lambda that we're given in the first part of the question, says 3 arrivals or 3 customers come to this ATM. So for our number of segments, that's given to us in part A, specifically in a given 15-minute segment, so only in one segment. We next have to find our lambda t, so I'm going to take my lambda of 3 times my t of 1, and that gives me lambda t of 3. This is the mean that we're going to use for Excel. So it can be a little bit confusing because we have the mean in our story, which is our lambda, but we also have our lambda t, which is the mean used for Excel. So just be aware. The event of interest, again, we have to convert our problem into a probability statement. And essentially we're going to write the probability that x equals 1. We have one customer coming to the ATM. So you can use Excel here. Here's the formula. It's equal Poisson.dist. Our x value we'll plug in should be 1. Right, so that came from our probability statement right here. The mean that we calculated is lambda times t. So that's 3, and we are working with an exact value, so we're going to use false. So you can type this directly into a cell to find the probability distribution. Now, if you prefer to use the formula builder, the formula builder will look like this. So you'll click on Formulas and Insert Function. Our x, we put in 1. Our mean, which is our lambda t, we'll put in 3. For cumulative, we're looking for an exact value, so we'll type false. And then we get the Poisson distribution at 0.1493 probability that exactly one person arrives. You can also watch me do this in Excel in a separate video if you want to see it demonstrated live. Let's do part B of the same story. What's the probability that fewer than 4 customers will arrive in a 30-minute segment? So we have to dissect again. The segment unit, according to our story, is still 15 minutes. That did not change. So you have to go back to the original story. 15 minutes is our segment definition. The mean is still 3 arrivals or 3 customers. That hasn't changed. That's our setup. However, what has changed in part B is the number of segments we're looking at. This time the number of segments, our t, is actually going to be 2 segments because 15 minutes fits into 30 minutes twice. So we're just doing a little bit of dividing to get that. And then our lambda t, we'll take our 3 times 2, and that gives us 6. Now for our event of interest, when we're given a problem, we want to make sure we understand how to rewrite it as a probability statement. Since it states fewer than 4 customers, that's the same as saying the probability that x is less than or equal to 3. Then using our Poisson distribution, we'll go ahead and plug in what we know. So our x, in this case, is 3. Our mean, which is our lambda t, is 6. And we are working with a cumulative probability since we're looking for fewer than 4 customers. So that'll be 0 customers, 1, 2, and 3 customers possible. So we'll type in true. Again, if you want to use the formula builder, you can just plug in our values, our x of 3, our mean of 6, and our cumulative true. Gives us the probability of 0.1512 for fewer than 4 customers arriving to the ATM in 30 minutes. If you have any questions, just let me know.